In this video, I will talk about solids of revolution, which will lead into the method of disk to find the volume of the solid. We're going to start with an area, a planar region, which you can imagine as a piece of cardboard. So let's say that we have this kind of half pear shape here. The cardboard is attached by one end here to a stick. This stick is called the axis of revolution. As you spin the stick, the area revolves and it sweeps out a region in space, such as this kind of squash pear shape that we have here. Now the problem is to find the volume of revolution, which is the volume of the region in space, which is swept out by this initial area that we started with. Now the simplest case, such as this one, is to find the volume by cutting the region up into circular slices. So now we're going to take that pear-shaped and we're going to cut it up with perpendicular slices to the axis. So let's say that starting over here, this is going to be A, and we'll also say from here is going to be B. And the radius of the slice, we're going to take out 1, is going to be R. Then its volume is going to be pi times r squared for the area of the circle, and then we need to multiply that by the thickness of this slice. Now, if we revolve that shape, that pear shape that we originally had, about the x-axis, then in the simplest case, the radius is given by a non-negative function r equal to f of x, and the volume is generated by revolving the area under the graph from x equals a to b. So let me go back to this picture over here. So let's say that this is the y-axis, and this is a, and this is b, and this is our function, y equals f of x. So when I rotate this about the axis, this distance here is going to be the radius of one slice. So as usual, we're going to divide this interval up from A to B, up into pieces. And the kth piece, let's say we pull this one out, it has a width of delta x sub k. And then in this interval, or in this piece, we're going to pick an x value, and we're going to say, let's say x sub k. Then the volume of this kth circular slice will be pi times f of x sub k. So we're going to take that function, plug it in as our r. We're going to square it, and then we also have to multiply this by the thickness, which will be delta x sub k. Now, that's just for the one slice. So the total volume is approximated by adding up the volumes of all these individual slices, as you can see from this picture up here. Now, if you have n slices, and we let the thickness delta x sub k of a typical slice to go to 0, then we're going to have the volume equaling to this limit from k equals 1 to n, pi times f of x sub k squared times delta x. So now this is the area of our circle, and then with this part here, this is going to be the volume of one slice. So if we sum up all of these slices, taking the limit as delta x k goes to 0, and I actually forgot to write that in here, so this should have an arrow going to 0. Then we get this volume here. So the expression on the right is a Riemann sum, and we know that the radius is equal to f of x. So we can change this into the volume is equal to the integral from a to b of pi times f of x all squared dx. So in the examples that we do, the axis of revolution will always be parallel to the x-axis or the y-axis. If the axis is parallel to the x-axis, then the thickness is going to be dx, and the axis is parallel to the y-axis, then the thickness is going to be dy. The radius, r, is the distance from the axis of revolution to the edge of the slice, and it will usually be given by a function specified in the problem, which determines the region which is being revolved. And you're going to see how this works in the examples below. In this first example, we're going to find the volume generated by rotating the area under y equals sine x, which I've already drawn here, from x equals 0 to pi. Now, when we rotate, it should give you something that looks like this, kind of like a lemon. So our volume is going to equal the integral from 0 to pi, and it's always going to be pi r squared, so this will be pi, and we think about what our radius is right here. That's going to be our y value, which is equal to sine x. So it's going to be pi r squared, which is going to be sine squared x dx. Now, this is actually an integral that we haven't ever encountered. So I'm going to do a little bit of work to show you here. So we're going to use the identity that cos 2x is equal to 1 minus 2 sine squared x. So cos 2x minus 1 equals negative 2 sine squared x. So we have sine squared x, and we divide everything by negative 2. So then I actually will have half, and I'm going to change the sign as well, okay, because I'm going to reverse the negative 1 and the cos 2x. So I'm going to have 1 minus cos 2x. Okay, so what I'm going to do is I'm going to replace this into the sine squared x. So we have the volume is equal to, and actually I'm going to move the pi out. So pi will be in the front. From 0 to pi, sine squared x is now going to be half 1 minus cos 2x and then dx. So now we have pi over 2, which I'm going to pull that out. And to do this cos 2x part, I'm going to do a U-substitution. I'll do that in a different color. So let u equal 2x. So du equals 2 dx. So du divided by 2 equals dx. All right, so at pi over 2, integrating from 0 to pi, I still have my 1. Oh, actually, I'm going to take away my upper limit, because when I plug in pi in for the x here, my u value is now going to be 2 pi. So I'm going to change my upper limit to 2 pi, and this will be minus cos u, and this will be du over 2. So now I can finally integrate. So this will be pi over 4, pulling the 2 from here to the front. And when I integrate, I'm going to get u minus sine u, integrating from 0 to 2 pi. So I get 2 pi minus sine 2 pi minus 0 minus sine 0. All right, so we can see that sine 2 pi is also 0, sine 0, 0. So all of these parts are going to be 0. We only have 2 pi left. So pi times 2 pi is going to be 2 pi squared over 4, which reduces to pi squared over 2. And this will be in units cubed because we're looking for the volume. All right, let's try another one where the graph isn't given. So when the graph isn't given, definitely you should draw a picture, a graph, to see what this looks like. So it says find the volume of f of x equal to x squared, rotated around the x-axis between 0 to 4. So we're first going to graph our parabola. And actually, let's change this so that our scaling will work better, because we need to go to 4. So 4 is over here, and we know that's going to be 16. So let's make every 2 squares to be 4. So we get 4, 8, 12, and 16. Okay, so this is a little bit better. So 1, we get 1, 2 is 4, 3 is 9, and then 4 is 16. Okay, so we need to imagine that this shape here, up to here, is rotated around the x-axis. So we're going to get points on the other side, which I'm going to draw symmetrically over here. Now, in 2D, it's hard to visualize this. So if we drew this in 3D, we wouldn't have something that looks like this. Okay. It's kind of like a cone, or maybe even a Hershey kiss on its side. So when we integrate, so we're going to find the volume, and this will be from 0 to 4. Pi, and our radius is this distance here. And our radius is the function, so it's going to be x squared, and remember it's pi r squared, and then dx. So we're going to integrate from 0 to 4, x to the 4 dx. So this gives us x to the power 5 over 5, integrating from 0 to 4. So we have pi 4 to the 5th over 5, which equals 1024 pi over 5 units cubed. Now, what happens if we rotate about the y-axis? So when we do that, the volume, let's say, becomes the integral from c to d, and pi, this time instead of f of x, we're going to say f of y all squared dy. And then remember that c and d are now going to be y value limits. So let's take this equation. We're going to find the volume formed by rotating the area bounded by y equals x squared, y equals 4, and we're going to rotate around the y-axis. Oops, not that y-axis. So it's bounded by y-axis. We're going to rotate it around the y-axis. So let's draw our parabola first. And it's going to be bounded by y equals 4, which is up here. And then this will be rotated around the y-axis, which is here. So we're going to get something that looks like this, which is, I guess, like a bullet shape. So because we're rotating with the y, we need to use dy, which also means that I need to change my function here. So I get plus or minus y is equal to, plus or minus root y is equal to x, which means that this distance here, this will be my radius. And if you think about it, we can say that the radius is equal to x, and here we can see that x is equal to root y. And we're going to take the positive component. So the volume is equal to, we're going to integrate, remember, with our limits being y, so it's going to be 0 to 4 pi r squared, and in case our radius is root y, so this will be root y all squared dy. So we get pi integrating from 0 to 4 y dy, and this works out nice, easy to integrate. We get y squared over 2 from 0 to 4. So plugging in the 4 squared is 16, pi over 2, which gives us 8 pi units cubed.